Thank you also very much for the introduction and the invitation to give you a presentation on a research project called Oekophalt, Physical-Chemical Fundamentals of Bitumen Aging for Economic Recycling of Asphalt Mixtures. As you can see, there are quite a lot of co-authors. It was a large research project that's been going on for the last 3 years, and I'm happy to give you some results of the project. What was the main motivation? Why did we even start with this project and the topic that we've been working on? It is, by definition, a so-called bridge project, partly publicly funded bridge project. And the idea is to bridge fundamental with applied research to give some background and to be able to use it for the construction practice in the further course. So we had a consortium consisting of our Institute of Transportation. We had people from materials chemistry and people from our Institute for Mechanics of Materials and Structures who were mainly working on modeling. It was, as I said, partly publicly funded by our National Research Promotion Agency, FFG, and also by industrial partners, Gestrata, Pitland Browserwetter, Svitelski, Niewelt, and OMV. So it was a quite nice consortium with industrial and scientific partners to work for some problems or open questions on bitumen aging. What we tried to do is we tried to find some more information on the background and reasons for bitumen aging. There are still a lot of open questions on that, and we tried to answer at least some of the questions. We also tried to find out the impact of bitumen aging on the performance of asphalt mixtures and tried to find a method how to assess the aging resistance of bituminous binders to be able to choose more aging resistant binders in the future. And then a future goal is to develop what we call actual bitumen rejuvenators based on the chemomechanics that we've been working on. For in the long run and the construction practice to be able to realize more or durable pavement structures, high recycling rates, what we call upcycling, not downcycling, which means using the reclaimed asphalt pavements not in low-level unbound layers, but to use a very high-quality product. Reclaimed asphalt is high-quality product, to be able to use it in an upcycling way, to be able to use it in bound new layers, again in quite high rates, and to produce high-quality recycled asphalt mixtures in the end. In this project, we worked on the first 3 items of the objectives that I've just told you. As I said, the project has parts that are more on the fundamental research. I mean, if you talk about fundamental research to a chemistry person or a physics person, they would say we're not fundamental at all. But for a civil engineering approach, it was quite fundamental. And then more applied research. There were various topics that we addressed, from microphysical explanation of bitumen aging to a micromechanical modeling to optimization of binder recovery, a new aging method for asphalt mixtures, and so on and so forth. I cannot take you to a journey through the complete project. It would take a little too long. I can just take you on a short trip and give you a glimpse of some ideas that we came up with, merely to raise your interest. And if you have interest in the project and the outcomes, there are a lot of publications out there to go into more detail. But what I would like to concentrate in this presentation are 3 items. First one, an revised explanation model on why and how bitumen is aging, some findings from field aging, especially on the low temperature behavior of asphalt mixtures for old asphalt pavements, and then some words on an alternative method for a laboratory aging method for asphalt mixtures. To start with the aging of bitumen, a microphysical explanation. If we look at bitumen on a macro level, we see a very nice liquid or viscous material with with great parameters, and it seems to be homogeneous. But if you look at bitumen on a lower scale, on a micro scale, we find out that bitumen is not a homogeneous material at all. We see a quite distinguished microstructure. You see two pictures here. The left one, the greener one, is from a laser scanning microscopy. So you see fluorescing particles within a matrix, a continuous matrix, and on the right hand of there is a picture of a so-called atomic force microscopy, something that is very popular right now. Everyone is doing atomic force microscopy. Unfortunately, it's not so easy to interpret the results, but still we get data and we will be able to interpret the results in the future. What we know now is we also see in those atomic force microscopy pictures distinguished phases. You can see there is a very small scale. You see there the scale for 2 micrometers. So we really go down into the micrometer scale, and you see there is what is usually called the Cantana phase or B phase. Especially from the right picture, the centers of those little cells look like bees. That's why they are also called B phase. Then there is a phase around these bees, a mantle phase, and these inclusions are dispersed within a matrix, within a continuous matrix. So we see, depending on the scale that we look at, we see 2 to 3 distinguished phases in our bitumen. And we tried to understand in a better way how aging really works in bitumen. And when I talked about aging, I'm talking about oxidative aging because we think that this is the most dominant part of aging in bitumen, of course also in asphalt mixes. When we look at bitumen microstructure and we zoom out a detail that you see in this picture, we see that we can distinguish different phases and that we can connect these phases with some chemical families. So we have these centers, the Bs, also called micelle centers, that we think are made up mainly out of asphaltines, so very highly polar material. Then we have the matrix, the continuous matrix around it, also called the melting phase. And if you take a look at the diagram to the right, it's a qualitative diagram, but still, you can see that we have in the explanation models that we have right now, there is a slight problem because we have the micelle center with the asphaltines, quite high polarity, and then we have the melting phase, the viscous liquid oily phase, the matrix, with a quite low polarity. But to get a working dispersion like milk, and bitumen is also a dispersion that works very well. That's why we have these nice properties that bitumen has. We need to have some phase in between that balances out the gap between high and low polarity, because without something like that we call mantle, we wouldn't get a working dispersion. So we have a mantle around it, mainly built up by higher polar aromatics. Now when oxidation starts, so when oxygen, ozone, nitric oxides, whatever is oxidizing our bitumen in the field, it wants to oxidize the most polar components, but it can't because the micelle center is surrounded by a mantle, so the oxidation, the aging, starts at this mantle, and actually it starts at the boundary between the mantle and the matrix, so it starts right here, and aging and oxidation means we get higher polar material, so the more a material oxidizes, the more polar material you get. And you can see that here with the orange line. This also means that we have now a very steep gradient of our polarity line, which means we get something like a temporary embrittlement. And this would mean if we would get a quite brittle bitumen in a very early stage. But the good thing about bitumen is, and about any material, at higher temperatures, the complete system gets more mobile, so all the faces get a higher mobility, and we get temperatures up to 55, 60 degrees in summertime in bitumen, which means all the faces get more mobile, and we can transport the high polar things towards the mesial center. So what we again get is a very nice, quite smooth line quite smooth line in our polarity, which means the dispersion works again, and temporary embrittlement is removed, and we still get a very smooth, nice bitumen as we know it. However, with long-term aging over decades and decades, more and more material ages, and we get a steeper and steeper increase in this change of polarity, and this means an increasing brittleness as we experience it with bitumen. But still, what we have to keep in mind with this explanation, that phases in bitumen first produce a temporary embrittlement that you see here with the yellow line, and then with higher temperatures in summer, or also when you heat up the bitumen again, and you get a smoother curve that you see in the blue line. This is something that can explain the healing effects that's been in the literature out there for a long time. And we know that bitumen and asphalt mixes can heal, but with this explanation model we can understand, or at least have an idea, why our bitumen is able to heal again and to overcome a certain amount of aging. So to sum up the first part, we see and think that embrittlement of aged bitumen is due to the gap in polarity that I just showed you within the bulk material. We have now an advanced model for the microstructure of bitumen, understanding better how chemistry is linked with the microstructure, and we have a sound model for explaining so-called healing effects. To go to the second part, findings from field aging, we took quite a lot of cores from road sections, mainly in Austria, with a very large variation of the age of the pavement. So we had pavements out there for 2 years, 7 years, but up to 20 and 25 years. So we found pavements where the surface layer is still active after 20 to 25 years in service. So we could really study the long-term aging also of surface layers that's been out there for 20-25 years. We carried out lots of different tests on that, but I would like to focus now on the low temperature behavior, because this is the part that is most important when it comes to field aging, at least in our climate region. What you see in this diagram is we already heard from a former speaker about TSRST, the cooling test, and the tensile strength test. So these are results from cooling tests, the TSRST tests, from different pavements. You can see on the left side we have results from pavements with a non-modified binder 7100 after 0 years, so shortly after laying and after 19 years in service, surface layer after 19 years in service. On the right side we have different asphalt mixtures, but all with similar polymer modified binder from 0 years, 7 years, 19 years to 24 years. And you can see the crack temperature on the bottom and the stress at the cracking on the top. If we concentrate on the crack temperature, it's quite interesting to see that even after 24 years, there is not a big change in the cracking temperature. I mean, we start at 32 to 33 degrees, if we look at the polymer modified binders, the green bars. But after 25 years in service, we still have 31 degrees, minus 31 degrees cracking temperature. So what we see is when we just look at thermally induced loading, so loading from weather, from temperature, there's quite a steady resistance. So the resistance to purely thermal loading in winter stays the same throughout the service life of a pavement. But if we take a look at this slide, and what you can see here is the tensile strength reserve. So this is a number or a value that gives you an information how much stress can be put on the pavement by traffic loading, in addition to the thermal loading by low temperatures. And you can see that this tensile strength reserve versus pavement age is reduced quite constantly year after year after year. So we see that the tensile strength reserve with increasing age decreases by around 2% per year. This is just for SBS modified binders. So after 20 to 25 years, we have around 50% of the initial strength reserve. And this means that the decreased low temperature resistance that we see for our aged pavements is not due to a decreased resistance to thermal loading, but a decreased resistance to the additional traffic loading. So a pavement that is aging can always withstand the same thermal loading. It can always withstand minus 30 degrees. If in the beginning it can stay at minus 30 degrees, it can be the same at the end of the lifetime. But the ability of a pavement to take up traffic loading in addition to the thermal loading decreases, and that's why we see more and more low temperature cracking with increasing age of a pavement. So I couldn't show you that because there was not enough time, but what we saw on the bitumen level, to sum that up, we saw on the bitumen level that field aging on the bitumen level stays constant after 10 to 12 years of aging. But we see that what we call structural aging, what I just showed you, continues over the service life of a pavement. And what we also saw from our analysis is that long-term field aging is basically limited to surface layers when we talk about dense layers. Of course, when we come to open-graded layers, there will be a certain amount of aging also on the binder layer below the surface layer. Last item that I would like to talk about is an alternative method for laboratory aging of asphalt mixtures. And there are one or two critical questions. Why do we even have to age asphalt mix specimens in the lab? I mean, we have RTFOT, we have PAV, so there are very nice standardized methods with a long history of experience for bitumen. So why do we want to age asphalt mix specimens in the lab? Well, it could be that we want to look and optimize the mix design at the stage of mix design in terms of getting the best durability that we can get, a high recyclability of the mix, and take care of that even in the beginning when we design our asphalt pavement or our asphalt mix. Then we can, of course, take into account impacts of mineralogy on aging. We know that different sources of aggregates have an impact on the long-term aging of pavements. We can take a look at that. And of course, we can assess the additives, rejuvenators, whatever is out there on products that should improve our pavements. We can assess that in small-scale lab tests before using it in large field trials. The other question is, why do we need another method for asphalt mix specimen aging? Because we know that there are more than 30, 40 different methods out there already. What we found is there are some drawbacks of some of the existing procedures. Some of the procedures that age asphalt mixtures age loose asphalt mixtures, and the specimens are compacted after aging. Some of the methods use high pressures, high temperatures that are just not realistic when we look at field aging, where we have a maximum of 60 degrees in summertime and not 100 or 130 degrees or 20 megapascals. So we tried to find an alternative method to work with compacted asphalt mix specimens to keep the temperature and pressure within realistic limits, but still somehow needed to increase our oxidation rate to get an efficient procedure. And this is what we came up with. It looks quite complicated, but I will guide you through. It's not complicated at all. A method that we now call Viennese aging procedure, VAPRO. In the center of the method, of course, there is an asphalt mix specimen. You can see this asphalt mix specimen. It's surrounded by a membrane, and it is within a triaxial cell, but there is only a very slight overpressure, and the overpressure is just here to press the membrane to the specimen so that the gas that we apply would flow through the specimens and not around it. So that's the only reason why it's in a triaxial cell. The whole thing is in a heating cabinet to produce the temperatures that we want to produce. We work with a standard compressed air supply, but this air supply, and that's the new thing about it is we put this compressed air through an ozone generator. So we produce an ozone-enriched air. The reason for that is we know that oxygen, atmospheric oxygen, is quite low in its oxidation ability at the temperatures that we have out there. 60 degrees, still atmospheric oxygen is not very active. But we know that ozone, nitric oxides, they are available in low quantities on the road, but still they are very, very oxidizing even at low temperatures. That's why we said, okay, let's increase the ozone concentration. It's something that is out there anyways, and we will just increase our oxidation rate without triggering any other aging mechanisms. So we increase the ozone level, we put it through a warmer just to get the right temperature of our aging gas, and then we let it flow through the specimen and have an exhaust hood so that the ozone-enriched air would not get into our laboratory air and age all the people and not the asphalt mix. That's the method, that's how it looks like. Of course, it's a prototype right now. You see the specimen in the triaxial cell, you see the heating coil, and the whole thing is within a heating cabinet. We carried out some validation on that. We carried out cyclic indirect tensile tests. We tested specimens before and after aging. We also extracted binder and did binder tests. What we see, without going into detail on this graph, we carried out tests at 45, 60, 75 degrees. We did aging from 1 day up to 6 days of aging. What we see is an increase in stiffness of the material, an increase in stiffness of the binder, and an increase in elasticity of the binder, so that the same things that we see out there in the road with field aging. So with VAPRO, we think that we have a quite realistic procedure for long-term aging of asphalt mixtures in the lab. By using ozone-enriched gas, we can reduce the aging temperatures to values that are also out there on the road in summer, maximum of 60 degrees. And with this method, we can bring an asphalt mix specimen within 4 days into a field-aged surface layers after 10 to 12 years of aging. So it's quite efficient, but still, it's a prototype and it's still ongoing. To give you some short words on summary and conclusions. We had some contribution and some new findings on the fundamental-based research, so we now have advanced or more sound models for the description, explanation, and prediction of bitumen aging. We did some extensive analysis and findings on field aging of bitumen and asphalt over 20 to 25 years in service. And we tried to bridge the results from fundamental to applied research and practice. We did some work on back distillation of PMB. I couldn't go into detail on that. We tried to find a more realistic procedure for long-term aging of asphalt mix specimens. And something that I could also not go into detail is that we tried to come up with a quick and dirty method for analyzing aging and aging resistance of bituminous binders. Again, this is a very short trip through the research project. If you're interested in more than what I showed you right now, just contact me or any of my colleagues or read one of the publications that are out there. But for right now, that's all from me. Thank you very much.